I want to talk about the Taqwaan problem from homework 2. This problem combines both conservation of momentum and relative velocity, which makes it a little bit trickier than other problems that only include one or the other. So the setup of the problem is you have a kid in a little car and he has a rock. The problem has two rocks, it doesn't matter. Let's just consider one rock. So he has a rock and he's just sitting here and his car has wheels, so he's free to roll without friction in either direction. That makes this a functionally isolated system. There are no forces acting in the x direction, so if he starts moving in the x direction with some speed, he'll stay moving with that speed. So he throws the rock, and in doing so, he's going to start to move, and that's because the net momentum for an isolated system is conserved. So initially, this is the initial state. He's just sitting there with a rock. So the initial momentum of the system, which we're defining to include the rock, the car, and the boy, is 0. And we can put a little x hat on that and define this to be the x hat direction. So the initial momentum is 0. So he throws the rock, he throws it to the left, so he's going to start moving to the right. And the picture is going to look like this. So what's the final momentum? Well, you say, well, it's 0. And that's totally true. It is 0 because it has to be the same as what it was when we started. But we can still write down the final momentum because the final momentum is going to be the momentum of the ball plus the momentum of the kid in the wagon. So we can write that as the momentum of the rock. So that's m, the mass of the rock times the velocity of the rock. And we need to add the mass of the wagon and the kid times the velocity of the wagon and the kid. Okay, great. So now the tricky part is when you're conserving momentum, you need to consider the velocities of the objects. And we know that velocities are always measured with respect to something else, even if it doesn't explicitly say that. So when you're conserving momentum, you have to stay in the same frame. So you have to say, okay, momentum is conserved in the frame of the ground, which means that the velocities that appear in this equation must be measured with respect to the same thing. They have to be measured with respect to the ground. So this equation is really the mass of the rock times the velocity of the rock with respect to the ground, plus the mass of the wagon and the kid times the velocity of the wagon and the kid with respect to the ground. Okay, so now, because momentum is conserved, the initial momentum, which was 0, has to be equal to the final momentum. So our initial momentum was 0, and our final momentum is this expression right here. So in this problem, we are looking for the velocity of the wagon with respect to the ground. That's what we want to find. We don't know the velocity of the rock with respect to the ground. In the problem, they told us that the speed of the rock was 8 meters per second with respect to the kid. And that speed is with respect to the kid once everything starts to move, because the rock only has a speed once it starts to move, which means that the kid is also moving as well. So we need to somehow use this to figure out what the velocity of the rock with respect to the ground is. So we don't know what this is, So I recommend just rewriting it as something else. So we're going to use the subscript squeeze. So this velocity, v rock with respect to ground, you can write that as the sum of two velocities. The velocity of the rock with respect to the third object here, which is the wagon, plus the velocity of the wagon with respect to the ground. And because these two W's are next to each other, we say they kind of squeeze together and disappear, so you're just left with VRG over here on the left. Okay, so do we know V rock with respect to the wagon? Yeah, we know that speed, so that's great. And do we know VWG? No, we don't know that, but that's what we want, so it's okay to have it in our equation. Another way to look at this is that we have two equations. We have one from conservation of momentum and one from relative velocity, so that gives us two equations with two unknowns. Okay, so let's substitute this expression in here. So we'll have 0 equals mr, and then we're just going to replace vrg with vrw plus vwg plus this other term. Now, we can combine this term with this term. Let me just write it out, make it a little easier. So I'm distributing this mass through this sum, so that's mr vrw plus mr vwg plus mw vwg. Okay, so now these two terms can combine. So the mass is the sum. The mass is times VWG. And now we can solve for the velocity of the wagon with respect to the ground by dividing both sides by this term after we subtract this from both sides. That will give us the velocity of the wagon with respect to the ground is negative the mass of the rock over the mass of the rock plus the mass of the wagon and the kid times v rock with respect to the wagon, which is that velocity corresponds to the speed that was given in the problem. Okay, so we're almost done. From here, we would just figure out the correct signs for all of these values, plug it in, and get a number. So we could do that. So I think the mass of the rock he threw was 10 kilograms. And I think that the weight of the wagon and the kid was 45 kilograms total. And the speed was 8 meters per second. Now, what was the direction that he threw the rock? Well, he threw it back. So this is a case where I really like to have an algebraic solution so that I can see what velocity, what sign is going to give me the answer, and then I can check that I have the sign correct. So this has to end up being a positive number. So I know that this is going to have to be negative to cancel with that to get a positive number. So then we're just going to get 80. The kilogram unit's going to cancel out. So we're going to get 80 over 55 meters per second, which is 1.45 meters per second. And this is in the positive x hat direction. And that's it.